today. So that's part 4. So we'll talk about Cheeger-Gromoll splitting theorem. Okay, so maybe a way to understand this thing is to ask the following question. So question. So recall that we have seen that when the Ricci curvature is bounded from below by something positive, then we get a diameter bound. A natural question would be, what does Meyer's theorem become when the curvature so here to be understood as the Ricci curvature is only non-negative. Non-negative. Well, in general, one cannot say much, but we will see that there is one case where things get really nice. And maybe let's try to make some picture here. So let's assume we have two infinite cylinders here and here. And let's assume we want to glue them together to fill here something. And we want to put, so this has non-negative curvature. This also has non-negative curvature. Let's assume we want to put some other piece in the middle while keeping the curvature non-negative. Well, actually, what we will prove, you can try to think a little bit. Okay, maybe I can try to start like this. So this has really positive curvature. But then you will have to go like this, and you will create negative curvature around here. So that's not a solution. And actually, there's only one solution to get positive curvature out of that, or non-negative curvature. It's just to go straight. And this will be a consequence of what we will prove here. So maybe let's write something. So only possibility with Ricci greater than 0. Okay. Okay, maybe first a definition before stating the theorem. So we will see why it applies in this situation, but geodesic, or actually a curve, that would automatically be a geodesic afterwards. A geodesic C, which is a complete geodesic defined for all time into a Riemannian manifold, is a line if, so for every Ts in R, the distance between C of t and C of s is equal to the absolute value of t minus s. So what is that? That says that your geodesic is actually minimizing on each of its compact parts. And it realizes the distance between any 2 points you pick on it. So, example of line. Here, when you start from here and go all the way to here, that's a line on the cylinder. And actually, as soon as you have two ends, you can play the following game. You pick 1 point going to infinity in one end, another point going to infinity in the other end. You take the geodesics between these points. You're in a complete manifold. You let the points go to infinity, and then all these geodesics will have to cross some compact set in the middle, so they cannot escape to infinity. And you can extract a subsequence, blah, 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 and get a line out of these points going to infinity. So in particular, when you have two ends or more, you always have a geodesic line like this. Okay. So maybe another definition. So a line, that's this way, but of interest is also the concept of ray, and that you can find in every non-compact manifold. So your curve is a ray if yeah, it's not defined on the same. So it's the same thing, but it goes from R plus to M, and the distance from C of t to, let's say, actually here C of 0 is enough, is equal to t. So that's something going to infinity like that. Maybe some pictures. So here, this is at the same time a line and a ray. Anything that wiggles around like that, any geodesic that goes like that, will never be neither a line nor a ray, because it will stop to be minimizing. If I take some kind of surface like that, you can find rays, more or less. They will look like that. That's a line. No, that's a ray. But actually, if you extend it, so you can find a lot of curves like that. So if it's rotationally symmetric, for instance, every intersection with a symmetry plane will give you another one. But what's going on is that if you try to extend it this way, at some point it will stop to be minimizing. So this is a ray and not a line. And once again, if you wiggle around, you're neither of that. Okay, so rays and lines gives, so this is something I won't deal with, but that gives you a way to capture the metric infinity of a Riemannian manifold. Okay. Well, now the theorem of the day. So that's by Cheeger and Gromoll. Okay, so first hypothesis, M and G is a complete, so I will stop writing complete everywhere, that will be assumed throughout. So if M and G has non-negative Ricci curvature, first hypothesis. Second hypothesis, if there exists C of t, a line in M and G, then Mn is isometric to some metric product, so maybe let's call that G, is isometric to some metric product R times some manifold dimension n minus 1, and the Riemannian metric is really a product metric. So this is an isometry. Okay, so that's the splitting theorem. So it tells you that if you have a line, then you split an R factor. So you can get quite a lot of mileage of this theorem. For instance, let's take Rn, and let's try to move a little bit the Euclidean metric, make a perturbation in some compact set. We keep everything else fixed, while keeping the Ricci curvature non-negative. Can it be done? Yes? No? Yes? Maybe? Well, actually, if you only move it inside some compact set, if you take straight lines which are far away, there will still be lines. So you will split some R factor metrically like that, and you will still be, you will have to be flat actually. And you can continue to play this game afterwards and so on. Okay. So.
Sorry? What does this R square?
So this means that, so here the tangent space split as a product of R and the tangent space to that guy. And so I denote here a point by R, and here by, let's say, P or something like that. So dr squared, so any tangent vector will be, well, some, so tangent vector will be some h, which is just a real number, more or less, and some v sub n, which is a tangent vector to n, and then g of, let's say, so I put this vector twice inside this, hvn will just be h squared plus the metric that I gave on Vn. More or less the matrix has splits. It's block diagonal with a 1 on top left, and then some other stuff which is basically this metric. So yeah, actually that's a good question. So why do I call that a metric product, and how can we recognize that in some other way? Maybe some more geometric way than just saying some metric has some precise form. You can play the following game. When you have a metric product like that, let's say you have, so let's consider some specialized value of R. So this is my R coordinate. Let's put a 0 here. And then this is, say, my manifold n. And so n times R is just a product. Okay, one thing you can play with, and one corollary of this form, and that can actually be used to define product of metric spaces, which you have probably already made, is the following. Let me pick some x here. Okay? Let me pick some y there in the R equals 0 copy of n. I want to compute the distance between x and y. Okay? So do as if this was like some kind of plane. What you could do is the following. So I project x in n. I take some z here, and I want to apply Pythagoras theorem. So some facts. So so this is, let's call that n0. So this would be the middle copy of n inside this product. So if Z is the closest point to X inside N0, then the minimizing geodesic from X to Z meets and not orthogonally. So basically what you need to show is that if you don't meet orthogonally, you can move a little bit the point Z and decrease the length. That's just what's going on here to prove this fact. And second fact, so what is the distance between these points? Actually, you can compute the length of a curve, like kind of assuming it's some kind of graph. You parameterize it by there, and you will see that the curve here, so let's call that maybe, well, R, I don't know. So yeah, this is my R function. So here the distance between those two guys is R of Z minus R of X. So R of Z minus R of X squared. So I can compute that if I know the function R. Here inside N, I'm going to write distances with that. dN of Y and Z. And let's put a square on top, and there, actually, what I draw is not that bad because you can make the computation inside that Pythagoras theorem holds. So that's dm of xy squared. So there are 2 points of view on these Riemannian products. Either you just say the metric has some special form, or more geometrically, this is equivalent to requiring that some form of Pythagoras theorem holds. Okay? So now let's try to prove this theorem. Maybe another application, kind of in the spirit of that. If you have more than 2 ends, then you will get several distinct lines which are not the same, basically. And if you think a little bit, so you must look like that for each one of these lines. And so when you are a product, so that means that you have something, maybe compact, maybe non-compact, and something like that. And actually, you cannot create a third end like that. It's not possible when you are a topological product this way. Either like the guy here is non-compact and you have only one end, or is that true? I guess, yeah. Or this is compact and you have exactly 2 ends. So any smooth manifold which has 3 ends or more cannot have a metric with non-negative Ricci curvature. Okay, so let's prove the theorem, and for that we will need some tool. Any question? No. Namely Boltzmann functions. So there are, well, I don't know if you are familiar with these objects. There are some sign problems for the definition. I pick one sign, don't ask me why. Okay, so the Boltzmann function is something which is associated with a ray, so with something which goes to infinity. So let C of t be a ray, then set b sub t of x to be equal to d of x, maybe this way it's better, d of c of t x minus t. So you look at you look far away, you look at the distance from x to some faraway point, but you want to extract a limit out of that when t goes to infinity, so you need some kind of rescaling. So with some small triangle inequality, you can do the following. So this is less, so let's assume that t is bigger than s and is bigger than 0. Then, so let's play a little bit with the triangle inequality. So bt of x, so, well, this is that. This will be greater than d, so that's bt, okay. I apply the triangle inequality here with c of x, c of s. So that d of x, c of s, plus c of s, plus d of c of s, c of t, and then I keep my minus t, okay? But what is that? That's, by definition of array, more or less. This is s minus t, t minus s, whatever you wish, and that's actually t minus s, since t is bigger than s. Okay, so t minus t. So this is greater than bs of x. So when you fix x, this is increasing. Oh, which, yeah, shouldn't stick to my notes. And that's much better, actually. That's right in this direction, okay? So that decreases when t increases. So, and playing in the same way with the triangle inequality, it's not too hard to show that it's bounded from below. So that you get a limit. So as t goes to infinity, bt goes to some function b. And b is called the Boozman function. Of the ray we are working with. So b is the Boozman function of my ray C. Okay, what property does it have? So if you look at each bt, so let us look at the Laplacian of bt. So that's what we do here. So Laplacian of bt will be less, at least where bt is smooth, but also in some weak sense. So, well, the t factor doesn't enter into play. So that will be n minus 1 over d of x c of t. So if I let t go to infinity, this will go to plus infinity. So this gives that Laplacian b is less than 0. Okay, that's nice. Another property, b. So the distance function is one Lipschitz. It's made for it. So BT, each of the BT is also one Lipschitz, and when you take a simple limit of one Lipschitz function, you also get something one Lipschitz. So B is one Lipschitz. Okay, do I need something else? So, as I said last time, so I've only proved the Laplacian comparison theorem outside of the cut locus. But here, to say something like that, you will need the full Laplacian comparison theorem, which extends up to the cut locus in a weak sense. Otherwise, well, the cut locus is moving with T. It's hard to say something. Okay. Do I need another property? Maybe. Well. Maybe that would be useful to have this other property. So, what is B of C of T naught for the thing that we have? So this is the limit as T go to plus infinity of, let's say, D of C of T naught C of T minus T. Okay? So T is going to infinity, so we might as well assume that it's bigger than T naught. So here, what is this distance? At least when T is really big, it's T minus T naught. Okay? So the T cancels out. So this is equal to minus T naught. Okay, in particular, if you follow the geodesic, that will tell you that the gradient of the Boozman function along this line is exactly, when you're on the ray that defines the Boozman function, it's exactly the tangent vector to the geodesic. Well, the opposite, actually. Okay. Okay, now what's going on when we have a line instead of a ray? So, if C from R to M is a line, well, when you have a line, you have two rays. That comes for free. Just look at what's going on the left and what's going on the right. So it defines two rays. So the first one I will call C plus, which is just, I go from R plus to M and I map T to C of T. And there's another ray, which is C minus, which will go from R plus also to M, and which will satisfy send T to C of minus T. So, and from this I get two Boozman functions. So one which I call B plus, and the other which I call B minus. So a crucial observation is the following. Lemma b plus b minus is identically equal to 0. Okay, so proof. Well, let's first look at what's going on at finite scale. Let's pick some x in M. And let's look at d of c of minus t x plus d of x c of t. Okay, so this, so let me try to do the triangle inequality in the good way that time. So this will be bigger than d of c of minus t c of t. Yes. And so by definition of a line, this is t minus, am I missing something? Minus t. Yeah, so that's 2t. Ah, okay, yeah. Now I take, so I will have some function b plus t and b minus t. So b plus, comma t. Oh, t is a bad idea here. Okay, maybe let's write that full-fledged. So b of c minus t x minus t. So when I take t going to infinity, I will get the Boozman function of the left side of my line. And then I take plus, same thing with that. So that will be greater than 0. Okay? And in the end, I will have that b plus of x plus b, well, be consistent, b minus of x plus b plus of x, from what I have here, is non-negative. Okay. So yeah, might need everything here, so I'll continue there. Sorry for the inconvenience. So we have that. Now, what's going on when we are on our geodesic? So what is b plus of c of t? Maybe let's call that t naught. Plus b minus of c of t naught. Well, we've seen that this was minus c naught, but since this is reversed, so yeah, maybe I should give the full proof. Yeah. Okay, so this is the limit as t goes to infinity of d of, so this is the right one. So c of t naught plus d of c of minus t c of t naught. And then I do that minus 2t. So here when t is really big, t naught is smaller. So yeah, here that's easy, that's just t minus t naught to get the absolute value. So limit. Here that will be minus t plus, oh. So that's absolute value of minus t naught. So that's minus t naught. Okay. Minus 2t. So if I did things right, here?
No, it's plus t, sorry.
Here?
Yes.
Yes.
T is down.
Okay. 2t, so yeah. 2t minus 2t, they cancel out. And that's a plus here?
Yes.
That's a plus here. Yeah. Okay, so that's what I was expecting. Everybody's canceling out. Okay. So, on this ray that we're considering, b plus b minus is equal to 0. So on C, b plus b minus is equal to 0. Oh. So it achieves its minimum. Now, so we have some Laplacian comparison going on. Recall that so Laplacian b for any Boozman function is less than 0. So Laplacian b plus b minus is less than 0. Okay? So what can we say from that? The maximum principle will tell us that on the whole of M, well, b plus b minus is equal to 0. So that's just the maximum principle. We have a superharmonic function which achieves its minimum. Okay, so once we have that, what can we say? Well, b plus is superharmonic, but it's also minus b minus, and b minus is also superharmonic. So b plus is actually harmonic. B plus, so yeah, let me write that in this way. So 0 is greater than the Laplacian of b plus, which is, from that, actually equal to minus the Laplacian of b minus, which is greater than 0. So b plus is harmonic. Laplacian b plus is 0. So I don't have time to do this theory, but that gives that it is smooth. Okay, and at least in this lecture, when we have a function, a harmonic function, what can we do with it? What has been our main tool? Buckner's formula, of course. Okay, so let's apply Buckner's formula. So 1/2 Laplacian gradient b plus squared is equal to, well, let's write the full formula. So gradient of Laplace b plus inner product gradient b plus plus Hessian b plus squared plus, so the last term is the Ricci curvature. Ricci curvature of gradient B plus, gradient B plus. Okay, so we have a harmonic function. This goes out. We have something which is which has non-negative Ricci curvature, so this goes down too. At least it has a sign. So 1/2 of the Laplacian of gradient B plus squared is equal to the Hessian of B plus squared. It's greater than that, which is greater than 0. Okay, but now, so what do we know about the function B plus? I guess the properties I need are still here. What do we know about the gradient of Boozman function? So it's 1 Lipschitz, so the gradient is less than 1. Okay, recall. So gradient B plus squared, and we can write that without any shame, since we know that our function is smooth, is less than 1. Okay. Gradient is less than 1. Moreover, so if I look at B plus of C of t, what did I get there? Was it t or minus t? I did this computation once, no? That's here. That's minus t. So here, the increase, so when you take gradient B, so you differentiate that. C prime of some t, this is equal to minus 1. So this is a unit speed geodesic, so this vector has length 1. So if I want the inner product to be minus 1, that means that on C, gradient B has to already be of norm 1. Okay? And it's subharmonic. It achieves its maximum, and it's constant. So on C, so once again, the maximum principle gives that. So what does it give? That the gradient B squared is equal to 1 on the whole of M. Okay. So this here actually vanishes. So then, so Hessian of B plus squared is identically equal to 0. Okay, what does that mean? So gradient B plus is equal to 1 everywhere. That means that B plus is a distance function. In particular, its gradient curves are geodesics. Okay? Now, let's go back to the Lie derivative. It's been a long time. Hessian of B plus is the Lie derivative of G in the direction of the gradient. So it is 0. Okay? So what does that mean? That means that gradient B plus is a killing field. Do we have some yeah. What's the sign of my Boozman function? Do I know something about that? Well, so let's pick some value of B plus. Well, actually, if my geodesic is defined starting at 0, yeah, I could take B of 0 makes sense. So let n0 be the set of P such that B plus of P is equal to 0. So I have my n here. Now, so yeah.
Your Laplacian of the mod of gradient of P plus squared is more than equal to 0. So how did you use the maximum process?
So Laplacian is positive and it attains its maximum. That means that it's constant. I'm right, no? Okay. Well, I get confused with that. At each time I have to think of x squared and what's going on, and then I get the right answer. Okay. So, but I don't know, maybe you've learned with some other convention on the Laplacian. That's done sometimes. And that messes things up. Okay. So we have that. So I have my n0, then I have my integral curve, so which are geodesics. Here, so this is, for instance, C of t, we'll do something like that. And when I move n0 by the gradient flow of my Boosman function, so I need to be careful. So B points in the opposite direction to my geodesic C. So if I push n for some amount of time, let's say S here, so this acts via isometry, so I will get another copy of n here with the same metric. Well, don't know why I'm being so slow. Basically, what's going on is, so here recall that since B plus is a distance function, then G can be written as, let's say, d s squared plus some metric h on each of the level sets here. That would be B plus equal to, yeah. Define ns to be the set of P where B plus is equal to S. Okay, and then with that, I know that d over ds of h sub ns, which stands for the Lie derivative in the direction of that, is equal to 0. So this doesn't move. D is ds squared plus h and 0. So, and my Boosman function is smooth, so I can do that as long as I want. So I'm done. Right. Okay. So that's the splitting theorem. Okay. So that's more or less the end of part 4. So part 5 is Cheeger and Kolding's almost splitting theorem. So this is the most recent result we will see here actually in this lecture, I guess. And it's from 97 or 96. Okay, theorem. So assume mi fixed dimension, let's say, gi pi. So Gromov-Hausdorff converges to some x dp, some metric space, and that so first hypothesis, the Ricci curvature of gi is greater than, say, minus 1 over I times gi. Second, so, oh yeah, that's something I didn't tell you. Some properties remain true when you have Gromov-Hausdorff convergence. So, some pretty weak properties, but nonetheless. The fact that here the distance comes from a way of measuring the length of curves carries on to the Gromov-Hausdorff limit. So we have a notion of length of curves on the limit. And if we have a notion of length of curves, we can have a notion of at least minimizing geodesics and so on. So we could say what a line would be. So xd admits a line. So it just means that, so let's see from R to X. So yeah, that's okay. So it just means that D of C of T, C of S, so that makes sense on any metric space, actually. But I assume that I have something like that. Oh yeah, if I want it to be a theorem, I should write a conclusion. Then what? Then there exists Y, a length metric space such that X is isometric to R times Y. Okay? So, what does it mean? That means that when you take Gromov-Hausdorff limit here, that, well, okay, the Ricci curvature is not quite non-negative, but almost. And so you expect the limit space to retain some properties of non-negative Ricci curvature. And here, this is one property which still holds. The Cheeger-Gromoll splitting theorem still holds for limit spaces, like that. Okay. So, let's try to think a bit about how we prove that. Well, we are not in a good shape to directly generalize the proof here because, well, we are not sure how to talk about, let's say, gradients here, let alone Laplacians, Hessians, vector fields, stuff like that. We really have a low amount of structure on that, just a metric space. So, and actually this, so we know it, nowadays we know that this metric space has more structure, but it would be cheating to use that because this theorem is the core of showing that this kind of metric spaces have more structure. So we cannot use that. So let's try to see what we can do. So let's assume that we want to prove the theorem, and let's try to go back to the definition of Gromov-Hausdorff convergence. So we fix R and epsilon, and we want, like, the balls around pi of radius r to be epsilon close to that guy, to ball of radius r inside that when I is big enough. Okay? And, well, that guy is here, so we need to recognize that. And we need to take into account this hypothesis. So I'll write something and I'll tell you it is equivalent. I won't tell you precisely why, but I hope that doesn't mean that's not too I hope that's not too bad. So this theorem will actually tell you the following thing. When you're far enough in a sequence which satisfies this hypothesis, then on some ball, so you pick some ball, some radius, and you assume you are far enough in the sequence, then you will more or less look like a product. Okay, so how to formalize that? So, must be really careful with the quantifiers here, so I'll take my notes. Okay. Laplacian, here. So fix n, so theorem. So for every dimension n, fixed, for every r greater than 0, big, for every eta, okay, greater than 0, there exists L, epsilon, and delta, all positive, such that if Mn G satisfies so it has Ricci, which is really not far from delta n minus 1 G. So delta is small here. So the Ricci curvature is almost non-negative. And then there exist 2 points. So I want to say, so if something Gromov-Hausdorff converge to something which has a line, then that means that when you go far enough, so basically there's a line here, there's my metric space which is going something, and I do have my sequence of manifold Gromov-Hausdorff converging to that. So if I want to Gromov-Hausdorff converge to something which has a line here, that means that the ends here have to stretch. And I need to, when I go far away in my sequence, to get points which are really far away from each other. Okay? And far away from the base point of my convergence. So that's what this next hypothesis will say. So there are 2 points which I'll call P plus and Q plus, and which satisfy. No. Let me try to be consistent. So Q minus, Q plus, and actually that's 3 points, because I need the base point too, and P in M. So these are 3 points in M with. Okay, so I need them to be far away from the base point. So P Q plus is greater than L, and P Q minus is greater than L. Also, I want them to be not close together. They should be, in some sense, there should be one q minus on one side of the base point P, and one q plus on the other side. So what could I, starting from now, since we'll do quite a lot of computation with distances and stuff like that, I'll use like absolute values for distances, okay? So second hypothesis tells you that they are on each. So P is kind of in the middle of Q plus and Q minus. And this can be quantified by some quantity which is called the excess. So this is Q plus P plus Q minus P minus Q plus Q minus, and I want that to be small. Okay? For instance, if P is on a minimizing geodesic from Q plus to Q minus, inside, in between, then this will be 0. So we will be in good shape. Okay, so these are the hypotheses. Okay. Then there exists a metric space Y such that be my ball inside M of center P and of radius R is, I will call that eta Gromov-Hausdorff close, means to some ball in, so did I? Well, I think I put the R in front. In some product metric space like that, centered at, well, some point, call that Q prime, and of the same radius. Okay. So, and what is that? So that's an effective version of Cheeger-Gromoll splitting theorem. So that tells you when the hypotheses of Cheeger-Gromoll theorem are not quite satisfied, but almost. Here the Ricci curvature has a negative but small lower bound, definitely small. And here you don't have a line, but you have a really long geodesic, and you're standing at the middle of this geodesic. Then, well, up to some error term, which is this Gromov-Hausdorff measurement of the error, you're almost a product at some fixed scale. Yeah, that's something which is, so basically I've had some arguing by contradiction under the rug and stuff like that. So yeah, what you really need to prove is that in the end, when you try to piece things together, well, you will be able to show the theorem. But that's the main step of the proof. Then showing that Y doesn't depend on the parameter, which is important, I agree. Or at least when the parameter go to infinity for R and 0 to for eta, that the same Y could be picked, will be done in the end.
This converge to line?
So it's not converges, it's close. It's eta, so eta is some positive number, Gromov-Hausdorff close. So the distance, the Gromov-Hausdorff distance between this and this is less than eta. That's what it means, okay? So, well, it's,
How to construct the metric space Y?
well, how did we construct n in the proof of, that was the level set of some Boozman function in the proof of Cheeger-Gromoll. Here we don't have light, we don't have Boozman functions, but we have points which are really far away. So we will play with them, and we will see what's going on. Okay, so I have 25 minutes left. Okay, so before trying to give you the steps of the proof of this, I want to give you a really complicated proof of Cheeger-Gromoll theorem. And actually, even a really complicated proof of Pythagoras theorem. So why would I do that? Well, maybe I'm sadistic, but that's none of your business. But the thing is that the tools we have used here for to prove Cheeger-Gromoll theorem were really smooth in nature. We needed vector fields, we needed Hessian, and we needed really good estimate. If the Hessian is not 0, in the proof I have made, what could you say about your vector field? Well, let's say we have L infinity bound on the Hessian, which we won't get in this proof. We will get some kind of integral estimate. So if we have L infinity bound, well, we will be able to say that the matrix doesn't wiggle too much or stuff like that. But that will be hard to use. And actually, even more crucial, the function we will be able to build will not be that smooth, not as smooth as the Boozman function we had here. So we need stuff which can deal with lower regularity situations. So let's recall. So we want to prove Pythagoras theorem. So observation. And basically, once you have understood this proof, you will see that this proof gives you some space to wiggle things a little bit and to say that, okay, when the hypotheses are not really satisfied but close, we can do something. So a stupid proof of Pythagoras theorem. Okay, so need to check my note for that, but okay, that's here. So assume we have some function b such that, so the same thing we got at the end of Cheeger-Gromoll. So Hessian of b is identically equal to 0. Gradient of b squared is identically equal to 1. Okay, so yeah, I don't need anything else. So pick some x inside M. Pick some y inside b minus 1, let's say of 0. Let's assume 0 is in the image of b. We can always translate stuff. Okay. So we have, so this is my b minus 1 of 0. I have some point y in here, and I have my point x in there. Yeah, maybe cheap colors. So how is the blue color? Is it visible or is it bad? That's okay? Okay. So that's my x point. Now, I want to show that there is some kind of distance structure that we can take. So I will take here z to be, so let Z be such that well, so what's going on? I want Z to be, so yeah, putting commas here, it doesn't need to be unique. The closest point to y, to x on, let's give a name to that. That's a hypersurface, let's call that sigma. On sigma. Okay. Now I want to show that some kind of Pythagoras theorem hold. And I'll do that with a variational method. So let me parameterize one of the geodesic. And let me parameterize the good one and not get stuff messed up. Okay. Okay, so that's the geodesic from Y to Z. Yeah. From Y to Z, really? So Y is in, oh, I wrote it the other way. Okay, here that would be from X to Z. Okay, let me pick another color. Did I use green? Not yet. So I will parameterize XZ. Oh, that's the same color. No, blue is used. Oh, orange. Fine. Okay. Okay, let's go from there to there. So that's, I call that C of S. I'm going from there to there with speed 1, let's say, and at 0 I'm at Z. At length of this geodesic, I'm at X. So what I want to estimate is this length minus this length. So let's say L is equal to so Zx. Okay, now, and let's put small l of S to be equal to the distance from Y to CS. To C of S. I'm cheating a little bit because, well, not yet actually. Okay. So what do we want? We want Pythagoras theorem. Whoops. So what we want is that, so at S equals 0, I'm here. Okay? Okay, so I'll try to write that in a good way. So little l of capital L is this length squared minus little l of 0, which is what's going on here, squared is equal to capital L squared. Guess I did that right. Okay. So now, well, that's what you tell to first-year students. If you want to show an equality, start with the most complicated side. So what is that? L of L squared minus L of 0 squared is equal to twice. So maybe let's put a 1/2 here. So it's the integral of its derivative from 0 to L. Okay. So this is something we haven't done, but when you study geodesics and stuff like that, you look at what's going on with that kind of of function on a Riemannian manifold. So what should that be? So should I give? Oh, I missed something, I guess. Okay, we'll see. Let me try. Okay, that's not too bad yet. Okay, well, maybe I'll use my notes. That won't be. That's a good idea, I guess. So L of S, I keep it that way. And there, what is that? The variation of length is, gamma. I have a gamma on my notes. I don't know who it is. Gamma is C, and I have CS. Yeah, that's even. Okay. I need to give a name to that geodesic. I'll call that gamma sub S, and I parameterize that by T. Okay. I told you it was stupidly complicated. So, first variation formula will tell you that here it's C prime of S, gamma prime S, computed at L of S. Yeah, ds. Why is that so? Because that gamma S, its length is L of S. Okay, so now what can I do with that? So when I'm on that direction, so what you can show actually is that along this geodesic, since it's the closest point to a level set of a distance function, the tangent vector to this geodesic is actually the gradient of the B function. You can show that. Okay, so that's the integral from 0 to L. So C prime is actually gradient B. L of S, gradient B, computed at C of S times gamma prime S at L of S ds. Okay, so now, let's do something even more stupid. So I will integrate. So I have a multiplication by L of S here. So I can integrate from 0 to L of S with respect to some dummy variable. What? Okay, maybe quick proof. From X to Z here, since it's the shortest curve, it's a geodesic. Since it's the closest point, the tangent vector here is orthogonal. So in particular, the tangent vector here is the gradient of B. That's what you were saying. But I told you at some point in the lecture that the flow curves of the gradient of a distance function are geodesics. By uniqueness of geodesics, it has to be the same curve. Okay? Okay, so let's introduce some dummy variable. Okay. So this is equal integral from 0 to L, integral from 0 to little l of S, and I keep that. Gradient B computed at the point C of S times gamma prime S of L of S, so dt ds. So, well, I've already used this hypothesis when I said this kind of stuff with the geodesics and so on. So here I need to have some Hessian. I need some Hessian to appear here. So how do I do that? Basically, you perform an integration by part, if I remember correctly. But with respect to which variable? That's the problem. This is okay. Oh, you'll see. It's some kind of magic, I guess. So 0 L of S. Yeah, I'll just do that. So gradient B computed. So C of S, what is that? It's gamma S of little l of S. And here I will replace that by gamma S of C of t. Okay? And then I replace that by gamma prime S of t dt ds. Why is that so? That seems strange. But the thing is that when you differentiate that with respect to t, since each of those guys are geodesic, what you will get is something like Hessian of gamma s. So that's gamma s of t, not gamma s of c of t. Oh, that's gamma s of t, I guess. Yeah. So when you differentiate that, what you get actually is the Hessian of B evaluated on the tangent vector to this guy. So that's 0. So that doesn't depend of t. So I can pick whatever t I want. That will still give me an equality. Okay, and what is that actually? Well, that's the derivative of B in the direction of gamma s. I need my note to make that clear, but when you sit and do the computation, that's pretty clear. So B of, and here you can do the computation. Gamma s computed at L of S minus B at gamma s of 0. Okay, what is gamma s of 0? ds. So basically what I did there is just recognize that this is B composed with gamma s of t and d over dt of that. Okay? So, well, I'll leave you alone afterwards. Now, B of gamma s, oh, no. Yeah, gamma s of L of S is C of S. And this is my, is it y or x? Is that x or y here? Gamma s of 0 is y. Okay, but if you look at B of C of S, once again, the gradient of B is the same as the tangent vector to the geodesic. So that will be S, more or less. Well, exactly. So this is, and since, that's the S, of course. Okay, B of gamma S of 0 is supposed to be 0. Okay? So yeah, let me finish that and then I'll leave you alone, I guess. So this guy, since I took this level set to start with, is 0. This guy is S. So then I integrate from 0 to L S ds. I get 1/2 of big L squared. Great. So took me a while to figure out this thing, but I thought I should try to explain that to you, because when you read Cheeger encoding or Cheeger's note or stuff like that, they do this calculation bare hands and they have to handle a lot of error terms and of wigglings and of saying, well, that goes in this way rather than that way. And they never presented that way. Well, I looked like a fool, like presenting it that way, but that's the idea that we will apply. We'll pick some closest point, some x, and we will move the geodesic from a geodesic inside our level set and push it like that and try to follow the derivatives to show that we indeed can say this kind of formula, which is Pythagoras' theorem, which defines metric products. Okay, I guess that's all for today. Thank you.